Okay, good morning or good evening, everyone, whatever. Thank you so much for joining us. My name is Yariv Bar. I'm from Matrix Israel, and I'm really excited to open here the first webinar, which is a global collaboration between RTI and Matrix. So for those who may not be familiar with RTI or Matrix, let me introduce the companies in a nutshell. First, RTI. RTI is a software company from the Silicon Valley that specializes in providing connectivity solutions for real-time systems. RTI offers a software framework called the Connect DDS, which stands for Data Distribution Service, that enables the development of scalable, distributed, and real-time applications. And about Matrix. Matrix is an Israeli information technology company founded in 2001 and based in Tel Aviv, Israel. Matrix provides a wide range of IT services and solutions to businesses across various industries. Matrix offers services in areas such as software development, IT infrastructures, cloud computing, cybersecurity, data management, and digital transformation. Matrix serves as the distributor of RTI in Israel for 12 years. Unfortunately, I can't hear the claps here, but I'm sure that there are plenty. Matrix works with leading companies in Israel. Together with RTI, we collaborate. We collaborate in aerospace and defense sector, medical and healthcare field, robotics, automotive, and wherever else necessary, we are there, along with the leading vendors in the market. In today's interconnected world, businesses rely on real-time collaboration. Whether it's remote team members working together, video conferencing, or instant messaging, a reliable and fast connection ensures smooth communication and efficient collaboration. We all talk about fast, high-quality, real-time communication. Let's see why we need good connectivity at all, with laugh.
4 candles. 4 candles.
Here you are. 4 candles.
No, 4 candles.
Well, there you are, 4 candles.
No, 4 candles. Handles for forks.
Okay, I'll stop it here, but and let's say a bit of seriousness. So in the next 55 minutes, we will learn how data-centric approach to system architecture can solve the challenge to help your maritime systems work as one using UMA, ROS, and DDS. ואני אגיד עכשיו בעברית, שביקשתי מהדוברים לא להתמקד רק בכלים ימיים, כי אני יודע שיש צופים גם מתעשיות אחרות, אז אנחנו נשתדל להתאים את עצמנו. Our speakers today are John Breitenbach, the Regional Field Application Engineer Manager at RTI, and Gal Schlesinger, the Head of Real-Time Technical Department at Matrix. So I wish you all a pleasant hour, and John, please, the stage is yours. Thank you.
Thank you, Yariv. Let me just share my desktop. Okay, is that coming through on your side?
Perfect.
Okay, great. So thank you all for joining us today. We're very excited to be doing our first joint session with our good friends at Matrix. As Yariv said, we've been working together for over a decade. So my name is John Breitenbach. And today we're going to talk about some of the cool things that our customers are doing in maritime environments. So let's dive right in. So this is the director of the movie Titanic, James Cameron, and he's one of the few humans, in addition to making movies, he's also a sort of hobbyist sea explorer. And he's one of the few humans that has actually been to Challenger Deep, which is the deepest part of the Mariana Trench. It's the deepest part of the ocean. And James points out that more people have walked on the surface of the moon than have been to Challenger Deep. And why is that? Well, the oceans are an unforgiving place, very challenging to get down to those depths. Of course, you may not have heard of James Cameron if it wasn't for this man. This is Bob Ballard, and this is the gentleman who actually found the wreck of the Titanic back in the 1980s. His work was actually funded by the US government, who was paying him to find a couple of sunken nuclear submarines. And they basically said, if you have money left over, you can go hunt for the Titanic. And Bob realized that humans traveling to the seafloor in a submarine isn't actually very practical. And as we've learned this past week at the site of the Titanic, actually, it's extremely dangerous. And Bob makes the comment about getting to work. He said, it was 2.5 hours down, and I'd get 2 or 3 hours on the seafloor and then 2.5 hours coming back up. And so basically for him, he described it as a 5-hour commute to go a mile. And so he quickly realized that the answer is in things like ROVs, remotely operated vessels. And this picture of him is actually in his command center in New England here in the US. And from here, he can watch and control ROVs all over the world, in oceans all over the world. And in addition to doing that, he can, from this command post, actually share that information, share the data with other oceanographers all over the world, including with school children, to try and captivate their imagination and try and grow up kids that are excited about engineering. So today we're going to talk about some of the applications where we're using autonomy in the oceans. And so it's good to talk about why the oceans are important to us. There are oceans and seas feed us, they provide us energy. We do a lot of commerce, a lot of shipping over waterways. Seas and oceans are vital to our defense. They're very large natural borders. And then, of course, that's just what we know. There's still so much exploration that needs to happen. I mean, our oceans and seas cover 70% of the Earth, and yet 80% of that remains unmapped, unobserved, and unexplored. Here in the US, actually 50% of US territory actually lies under the sea, and virtually all of it is unmapped and untapped. So we're going to talk through a few applications where some of our products are being used today in maritime applications, and then we'll turn it over to Gal to do a little bit more of a technical deep dive. So our oceans feed us. Let's talk about the Internet of Fish. Aquaculture, or aquafarming, is all about cultivating freshwater and saltwater populations under controlled conditions. So if you go to a restaurant today or the supermarket and you buy an ocean fish today, there's roughly a 50% chance that the fish was raised in an aquaculture environment like this one. Now, this particular one is off the north coast of Norway, about 500 kilometers north of Oslo. And here, baby salmon are hatched in onshore hatcheries, raised there for the first 6 months or so of their lives, and then they're transferred to these offshore facilities to be raised to maturity. The fish live here for up to 2 years, during which time humans are responsible for their health and well-being. And it looks peaceful and relatively low tech on the surface, but below the surface, there's actually a lot going on. It's a pretty sophisticated system. So there is a sophisticated Internet of Ocean things caring for the fish. Now, when you hear the word net when describing fish farms, you probably have one image of a net in your mind. But there's entirely different types of nets at work here. In this case, it's neural nets. So smart cameras use neural nets to recognize and monitor the school of fish. What the cameras are seeing, the data, is actually more important than the pixels in the images themselves. So in the upper left-hand corner, there's a neural net that is looking at the density of the entire school of fish. In the lower left, another camera trained with a different neural net monitors the amount of food in the water. There's food pellets that they use to feed the school. And this is critical because food is actually their biggest expense. In the upper right, you can see that individual fish are identified. And here we're looking for something very specific. They're looking for a parasite called sea lice. And so while feeding is the biggest cost associated with aquaculture, the second biggest cost is actually these parasites, the sea lice on the salmon. Sea lice cost the industry over $2 billion a year. So what can be done? Well, as part of the underwater Internet of Things system, these devices are being deployed, and these are underwater cameras. And they basically use the same type of neural nets, this time trained on the shape of the sea lice. And they use that information to actually target lasers to kill the lice on the fish while they're swimming by. Now, if you're in the defense industry, this should all sound really familiar, right? We have a variety of different sensors. They could be vision-based, they could be radar, they could be LiDAR, they could be sonar, that are scanning the environment, identifying targets, and then passing that information over to effectors that could be kinetic or non-kinetic. In this case, it's directed energy, but it's the exact same problem. And this is enabled by the fact that we're sharing data between cameras and effectors, sensors and effectors. Hey, our oceans power us. Increasingly, we are getting more and more energy from the ocean. RTI works with Siemens Gamesa. These are one of the world's largest wind turbine manufacturers. They make offshore wind farms as well as onshore. In these large wind farms, the turbines must work together as one, monitoring the upwind turbines and letting the downwind ones know about local conditions. And this is for gust mitigation, for power optimization across the array. But who is upwind and downwind changes as the wind shifts, right? So as the heading of the wind changes, I need to send information to somebody different and perhaps receive information from somebody different. And data-centric communications is what allows the data to always flow in the proper downwind direction at all times. Gal is going to talk a little bit more in a bit about what exactly that means. Getting a little bit of feedback here. I think somebody needs to mute.
Yariv, I think it's from your end.
Okay, that's better. Okay. Technique FMC rather. These guys are a world leader in offshore automation. They have these amazing ROVs. They can operate thousands of meters below the surface while the operators are safely up on a ship on the surface. Now, historically, these have been teleoperated, although more and more they're moving autonomy down into the ROVs. It used to be very much humans in the loop driving them manually, but now humans are more on the loop in a supervisory role. And we may eventually get humans completely out of the loop for some function. They might be fully autonomous. And this is because as computing power gets smaller and more powerful, they can actually put more computing power down in the pressure vessel inside the ROV. What's interesting is because they've taken a data-centric approach to this, it's actually transparent whether something like an autonomy algorithm resides on the surface in a computer on the surface or actually resides in the vessel. And we'll see how in a little bit that data-centric approach allows you to build a microservices-based architecture that allows the services to move freely anywhere on the network. So our oceans connect us. There are some 11 billion tons of goods that are transported by ship each year. And if you take the 11 billion, you divide it by the current world population, that means that each and every person on this webinar gets an impressive 1.5 tons of goods shipped over the seas every single year. So shipping's capacity to transfer goods and materials from where they're produced to where they're ultimately going to be consumed underpins modern life, right? We're a hugely interconnected world. So as of 2019, the total value of the annual world shipping trade had reached more than 14 trillion US dollars. And ships are becoming increasingly autonomous. We've seen what happens in recent years with manually piloted ships going through critical choke points like the Suez Canal. So in the not too distant future, you're going to see more and more autonomy. And here too, RTI works with some of the most progressive shipbuilders, including Ulstein. The control system and helm in this ship is absolutely amazing. It gives the captain a complete 360-degree situational awareness in an easy to understand interface. The ship is loaded with sensors and effectors that are scattered throughout the ship. They all communicate over redundant networks. And the ship now, once all of the sensors and effectors are connected over a network and we're exchanging data, they've found that it has been relatively easy to start to layer in autonomy, right? So they can program the ship to actually perform many maneuver operations semi-autonomously. And this too is enabled by that data-centric approach. So our oceans and seas are some of our greatest natural defenses. And because they feed us, empower us, and connect us, we have to defend them. And here too, RTI has a deep history in defense. RTI powers defensive systems across the US naval surface fleet and those of our allies. The Navy is changing though, moving from large manned platforms like you see here to smaller autonomous and remotely operated vessels. And in the future, the Navy is going to be built very differently. There will be small autonomous platforms that serve as remote platforms for remote sensors, remote effectors. Those will operate at the forward positions while there will be smaller manned craft at a safe standoff distance. And essentially those autonomous systems are going to serve as extensions to the manned systems. So this is just one of the US Navy's current autonomous vessels. This one is called Nomad. It's a supply ship. It has traveled thousands of nautical miles autonomously. And if you're creating or interested in autonomous surface vessels or autonomous underwater vessels, UUVs, these are both areas where our products can help. You might be interested in something called the Unmanned Maritime Autonomy Architecture, or UMA. There is a public version of the UMA specification that can be found on the AUVSI website. If anybody is interested in that, just reach out to Matrix and they'll get you connected. So with that, let's see, we've seen sort of a sampling of different types of systems, from aquaculture to underwater exploration towards offshore energy and defense. So let's see how we can make systems like these. There's a common thread through all of these, and it really comes down to the data. So with that, I'm going to turn it over to Gal from Matrix to explain. Gal?
Hey, thank you, John. Let me share the screen. Yeah, so everybody can see it, right? Okay, great. So hi, everybody. So thank you, John, for the introduction and the overview on the project. So I will, in the 15 minutes that I have, I will provide a short overview on the technical aspects of DDS concepts and capabilities, especially relevant for autonomy in general and for naval autonomy. Let's start with it. So one of the first concepts that I want to review is the concept of data centricity. When we look on a system, it could be an ROV and any unmanned system. It usually has a lot of sensors and actuators. Some of them can be remote, like if we look on the slide, we have, for example, a radar or a global positioning system, those kind of things. We have an actuators like propulsion systems, etc. And we could also have a teleoperation system, which of course is teleoperated could be in the local area network, and it could be also remotely on the wide area network, which is something that we will also discuss. And all those systems need eventually to communicate between each other, but eventually, and this is what I will expand about the DDS concept, we eventually have a conceptual data bus, which is a global data space for all systems to share the data between themselves. The concept of data centricity lies underneath in the concept of publish subscribe, which means that we are eventually talking not a system to a system, but we are talking to a topic or a global data space, a conceptual data space, which all the data is shared. So if, for example, we have the global positioning system or the sensor sense data, which is relevant for the propulsion systems or the teleoperation system, DDS creates this virtual data space where each system is only subscribes and publishes the data that is relevant for it. And then the system and the DDS will make sure that each system will receive it as it requires. So this is a very basic example of the concept of publish subscriber and data centricity. But then let's scale it up. If, for example, we can also, as I said, we can, again, each system can also publish every data that you want and also subscribe to every data that it wants. It's a multi-directional data sharing mechanism. And again, we can also have a lot of other use cases under this concept of data centricity. For example, one of the main features that DDS provides is the concept of late joiner applications. Again, when we look on the system, some applications or system can turn on and turn off during the whole system operation, and they want to recover from this data. So this is one of the things that our DDS enables as part of this concept. And again, the data sharing, as I said, is transparent to the application. This is one of the main concepts of DDS. So from the application perspective, it only publishes and subscribes to data. All the complexities of the data distribution and the late joining applications and all the other features of which I will mention in a few minutes, all of them are provided to the user, to the person who writes the code or designs the system as a set of configurations, which are referred to in DDS as quality of service. And again, one of the other features that DDS has is the concept of redundancy. So we could have a lot of propulsion systems. Maybe one is a backup for the other. And we want a transparent, like so-called hot backup between those systems. So this is one of the features that also DDS enables that to do it. On top of all of that, when we look on the data centricity concept, DDS provides us the mechanism to define a data model. DDS as itself does not define a data model. UMA as a standard does define a data model, similar to other standards that are out there, like robot operating system, ROS, or GVA, or FACE. A lot of standards use DDS as the foundation for their own standards and provide the data model and all the other complementary requirements on top of that. But again, you can use any data model you want using DDS. And using this data model, DDS provides you a lot of mechanisms that, because of DDS that knows the data model, when you create a DDS application, the data model is part of the acknowledgement of DDS when it operates in the system, in the bus. And due to this fact, DDS provides a lot of distribution-related capabilities that are very unique, like prioritizing messages according to the content, filtering data, and avoiding any network load that is not required, and a lot of features that are only capable by DDS because DDS knows what the data that is transmitted over the network, which is one of the main key features that DDS provides. knowing the data, which is part of the data centricity concept, provides the DDS all the capabilities and a lot of capabilities that you will need to develop on the application level. But because DDS knows the data, it allows you to implement it and to use it very transparently to the application level. So as I mentioned before, DDS provides a lot of features and quality of services that we can use in order to create much more elegant and much more simple application from the design perspective and from the development perspective. Let's say, for example, we have an algorithm, a path planning algorithm that requires some data from the sensor or from any other system. You can just tell DDS as a basic API, please provide me the data from the sensor only on a specific terms. And DDS will only send the data. Again, it will only send the data to this path planning algorithm only when the data is in this as the application required so. And again, it can change dynamically, and this is one of the main features that DDS provides. And again, we have a lot of other features in DDS, like making sure that the data is sent reliably. Again, not all the data is required to be sent reliably. We can have some data which can be lost from time to time because it's a high rate data or that is not that relevant. There are some data that we need to make sure that it received on the other end, like special commands or requests. And again, this is one of, again, a lot of features that DDS provides to build a very complex system and to do it very simply. Okay. Last thing before we move to the next slide, and I will mention it later on, is the concept of security. Now, this is a very big topic, but on top of all this publish subscribe architecture, DDS provides the way to implement a fully decentralized security scheme. So all the capabilities related to encryption and authentication and access control, DDS can provide those on top of that. And again, everything is transparent to the application level. Again, everything is provided via quality of service or a set of configurations and artifacts that DDS uses. And from the application perspective, the code doesn't change. So when we look on the data stream between, for example, a teleoperation system and the ROV or the UAV, again, it doesn't matter. We usually have a very constrained network stream. And this network stream is not only constrained, it could have errors, disconnections, variable network bandwidth, and a lot of issues. And on this bandwidth and this data link that we have, we need to push a lot of data. And not all data is equal. Again, we have some data, for example, if you want to send raw data like frames or video, we could lose some frames from time to time because we want to prioritize from an application perspective, we want to prioritize commands which are much more critical, and sensor data, we want to receive it, but again, we cannot lose more than 1 second of data from the sensor side. So this kind of requirement can be very easily translated to a DDS quality of services, like a built-in mechanism of prioritization in DDS, a flow controlling mechanism, which is also built into DDS, the filtering mechanism, which I also mentioned before. All those things are implemented within DDS and are provided for the user in a very simple configuration. And this is only a taste of all the quality of services, and I mentioned some of them before, but again, we don't have a lot of time to go over all of them, but all those features are critical to build a very complex and dynamic system, which allows us to, again, save a lot of effort from the development perspective, because we don't need to develop those very basic or necessary requirements and capabilities, and we can already use DDS, which has all those features built in. So one of the features that I want to mention and go into it a bit more is when we want to scale up. So when we scale up or scale out, eventually we want to, our system is much more complex. For example, if we want to scale out from the network perspective, not all the systems eventually which we want to communicate will be available in the same network. Sometimes the network is much more complex because we're working under a wide area network. And again, it could be a wide area network like the internet or a managed wide area network in the cloud. It could be very complex configurations, and the system is not so-called flat from a network perspective. So DDS has a lot of capabilities regarding the ability to support from working in a local area network to work in the cloud, in the wide area network, and allows every system to communicate between each other. And I will go into it a little bit more later when we go into a use case of a remote teleoperation for a UAV or an ROV. So this company, which is called Mission Robotics, it's a company which develops, I won't get into all the details, but eventually develops an ROV, which in the initial development of the system, they were developing and curating a teleoperation system, which was deployed in the local area network where the ROV was deployed. But as the things progressed and the system evolved, they wanted to allow for the system to be able to teleoperate the system, the ROV, from a remote location, not near the ROV, from the office or abroad, it doesn't matter. And using DDS real-time wide area network feature, they were able to do it with minimal effort in a few hours, only by, again, simple configuration in DDS quality of service to allow every system, like the teleoperation system and all the subsystems within the ROV, to communicate remotely, and again, without any change or in the actual application code. And all of this was possible, again, as I mentioned, using RTI's real-time wide area network connectivity solution, which is a set of features which allows DDS to work under the complex and a very complex wide area network in the internet, under a lot of NAT and network roaming issues that are present in the internet, and to allow to communicate without any requirements for multicast, which is sometimes used by DDS in a local area network, and all of this under the same security policies which are usually required when when communicate on top of the wide area network. So there are many use cases which DDS can and is deployed at the moment in various configurations of connectivity on top of the wide area network. We can do communications like edge to data center, which we want to aggregate a lot of data and maybe teleoperate from a central location, a lot of remotely operated systems. We can also maybe have a use case when an ROV wants to communicate with another ROV over the wide area network. So we want to have this mesh-like network and to allow DDS to support it. So we have a lot of configurations that DDS supports, and this is just a simple taste of the features that DDS allows in this area. So as I said, eventually when we look on the DDS environment, DDS eventually is a software library. It's a standard for a publish subscribe architecture. It has a standard API for the user in a lot of SDKs like C, C++, C#, Java, etc. And a very rich protocol, which provides all this publish subscribe and all the features that I mentioned before. All of them eventually from the user perspective or the developer perspective is transparent to the application because you are working with a standard publish subscribe API. And whether you choose to use DDS with the default UDP configuration, or you decide to move to the WAN and use DDS underlying real-time WAN transport, or if you develop everything on a simple PC or a containerized machine, everything can work with shared memory. All of those capabilities are transparent to the application and are only provided to you via a simple configuration. And all of this is eventually, as I said, is very simple to use, and from the application perspective, using all the DDS quality of service. So just to summarize things up, when we look on the DDS product suite, again, we only discussed a bit about the DDS SDK and DDS Secure, but eventually when we look on the RTI product suite, it comes with a lot of additional tools which allows you to easily integrate and to test and to emulate data within your system, because it's not only about the development aspect, but it's also about the integration steps and the testing phases. So RTI provides, as part of its software product suite, a lot of complementary tools to allow you to easily integrate and to develop your system. One of the tools, which this is what I will finish with, is one of the major tools in DDS, in RTI, is the admin console, which is a big product, which, as you can see, it's only a snippet from this application, which provides you a full visualization of all the DDS bus, which you can see all the data that is sent and received in the network, which topics are currently present in the network, which applications are up, if there is any issues in any applications from a connectivity perspective, or from a logging or resource from a resource aspect. All those things are transparent to you and handed to the user or the integrator or the developer to see and to visualize all the data and to allow you to easily integrate and perform any tests and any verification that you want to perform as part of the development of the system. So this is like a simple snippet of what one of the tools that RTIs have to allow you to for the simple integration. And I think, and I will finish with that. Yes.
Thank you, Gal. It was fascinating. And thank you, John, of course. And I see that we have some questions. Irene, can you help us with reading those questions? I don't know where Irene is.
Sorry, no, I was trying to set up my microphone that was out, so sorry.
Okay, perfect.
So the first question is, do you work with robotic operating system?
Yeah, so John, do you want me to answer that, or do you want to answer it, John? Okay, so sure, no. Yeah, so DDS eventually, ROS, or specifically ROS2, uses DDS as the underlying framework for connectivity. It does provide a lot of features, added features on top of DDS, because it is a so-called operating system for robotics. But the connectivity framework for ROS is DDS based. And due to this fact, any tools or any native DDS application can very easily communicate with any ROS-based system. So the short answer is yes.
All right. The second question that we received is, what about security?
Okay, so as I mentioned before, DDS, I won't get into much details, but DDS does have a lot of features as part of the DDS security spec. I will just highlight the main features. So DDS does have a built-in authentication mechanism. It has the built-in cryptography mechanism, which is providing us the ways to encrypt a message and to sign a message. And we have one of the unique features in DDS regarding security is the access control feature, which this access control feature provides the user the ability to set some sort of a security policy, which we could see it as a security policy, which each application can define if it has access to a specific DDS domain or a topic. Let's say I want a specific application to only have access to write to a specific topic and only read from another topic. So this one is one of the main features that DDS has to allow us to enforce that, so to make sure that every system behaves as it should be.
All right, so I think those are all the questions that we received. I don't know if any other attendees wants to send any other question in the meantime.
Okay, that's fine. And if you have more questions, please feel free to contact us, and we can, of course, we can answer it offline. On behalf of RTI and Matrix, thank you all for joining us. It was our pleasure. Thank you, John. Thank you, Gal, and thank you so much, Irene, for producing this webinar. And have a great day. Bye-bye.
Goodbye,
Thanks,
everybody.
everyone.
Bye.